Have you ever wondered what lies behind world-changing innovations? It might not always be the billion-dollar machines in the world's most complex laboratories. Instead, it might start with something as simple as a piece of Scotch tape and a few flakes of carbon. In 2018, the world of physics was shaken by a discovery that sounded like a high school science project. Researchers found that the most ordinary materials, when stacked and twisted at a precise angle of just 1.1 degrees, could become superconductors that conduct electricity perfectly with zero resistance. Welcome to the era of Twistronics, a new discipline telling us that geometry and the angle of a twist are just as important as chemical composition. And today, I will take you to meet the real hero hidden in the shadows, a material as white as powder and as simple as a cosmetic ingredient. Yet it is the key to building supercomputers that work at room temperature. That material is hexagonal boron nitride, or what scientists call white graphene. When we talk about wonder materials, many think of graphene, the one atom-thick sheet of carbon that earned a Nobel Prize. Graphene is incredibly strong and conducts electricity brilliantly, but its fatal flaw is that its electrical flow is hard to control, like a dam without a gate. That is why the world needs white graphene, or hBN, to step in. hBN has a honeycomb structure very similar to graphene, but it is made of alternating boron and nitrogen atoms. The thing that makes it fundamentally different is, while graphene is a great conductor, hBN is a superb electrical insulator. And this is the missing piece of the puzzle, because in the world of electronics, we don't just need a highway for electrons to race down. We need shoulders and firewalls to keep them in check. The magic begins when we stack these ultra-thin sheets together. Imagine two window screens laid on top of each other. As you start to rotate the top layer just slightly, a new and complex pattern emerges. Scientists call this a Moiré pattern. These Moiré patterns completely change how electrons behave, especially at the magic angle of 1.1 degrees. At this point, electrons slow down until they almost stand still, and in that state, strange quantum phenomena occur, like superconductivity, which means electricity flows without losing even a tiny bit of energy. Think about it. If the wires in our homes or the batteries in our phones generated no heat, how much energy could we save globally? For corporate employees who rely on technology every day, hBN is closer than you think. Currently, companies like Samsung and Intel are investing heavily to study it, because hBN conducts heat exceptionally well while remaining an insulator, making it the ideal material for cooling the next generation of smaller, faster processor chips. For parents at home, hBN is also right there in your daily life. It is a key ingredient in cosmetics like eyeshadow and lipstick, chosen for its smooth texture and safety for the body. But in the near future, hBN will do even more. Researchers have successfully created the world's first deep ultraviolet LED from hBN, which is highly efficient at destroying viruses and bacteria. Soon, we might have water filters or air purifiers embedded with this technology, ensuring the safety of everyone in the family. However, producing high-quality white graphene is no easy task. While hBN has been used in industry for a long time as a lubricant, creating atomically thin, perfect sheets is much more complex than graphene. We have to control the balance of two different atoms to arrange them in a precise alternating pattern. The process known as CVD, or chemical vapor deposition, is like growing crystals out of thin air, requiring incredibly precise calculations. But the good news is, we are entering an era where artificial intelligence plays a major role. Instead of spending a decade on trial and error in the lab, we are now using machine learning to find these magic angles and new material structures, accelerating the pace of discovery by 1,000 times. The greatest challenge now is turning these beautiful laboratory results that often require extreme cold into practical technology that works at room temperature in our daily lives. Every piece of data I've analyzed points to the same conclusion. We are shifting away from focusing solely on chemical ingredients towards the engineering of atomic structures, what we call designer matter. We are no longer searching for rare new materials. We are learning how to twist what we already have to unlock the power hidden within. Finally, I want you all to imagine this:
A world where computers are 1,000 times faster but generate no heat. A world where clean energy can be transmitted across the globe with zero loss. All of this could start from twisting a thin sheet of this white powdery material. The era of Twistronics has begun, and it is redefining the limits of what is possible in our world forever. Thank you for joining us on this journey into the tiny world of atoms, and I will see you again in the next innovation.